Okay, friends, in our last class, what we have seen is how to obtain the member stiffness matrix for the spring. Also, we have seen that how to obtain the total stiffness matrix for the assemblage of the spring using things, two principles. One is we have derived from the principle of equilibrium and superposition, and first physical principle we have seen how to obtain the total stiffness matrix of the assembled spring system. Second method we have seen that how to add do the addition of the spring assemblage and stiffness matrix of the individual springs using direct method. Okay, using individual springs stiffness equations, and how do we use that individual spring stiffness to get the total stiffness matrix for the spring assemblage. Now we will, in today's class, we will learn one typical example which will give you some idea how do you obtain the how do you get the solution of the problem. So let us consider the spring which is having one end fix. We have to determine the global, of course, the global stiffness matrix using the direct stiffness method, then also the displacements and the reactive forces. So of course, as I told you, the nodal nodes, the joints of the spring are to be numbered. In this case, I'm numbering the joints of the spring stiffness random numbers. Okay, so that is 1, 3. So this will give you some idea, 4 and 2. And the constants of the springs are given as K1 is equal to 200 Newton per mm, K2 is equal to 400 Newton per mm, K3 is equal to 600 Newton per mm. And let us assume, of course, there has to be some external loadings. So let us assume that there will be 25 kilonewton, which is the load which is acting in the positive x direction, as 25 kilonewton of the load. And let us name the spring individual member, name it 1, 2 and 3. Okay, now we begin writing the individual spring stiffness. So that is, of course, K1 3, K1 3 for the first member. We will be writing the, as per our formula, we have seen that K minus K minus KK. This was our formula. So in this form, it was easy to write. Of course, you write the number here for, easy view. We can write 200 stiffness coefficient, which is given 200. So we can write it here 200 minus 200 minus 200, 200. Then K34. K34 will be written in a similar way. It is 400 minus 400 minus 400, 400. And then last one, K4, 2. Of course, don't forget to add here 3 and 4, 3 and 4. The last one is K4, 2 is 600 minus 600. This node numbering has to be followed properly, 1, 3, 4, 2. Okay, minus, because this way we have to be careful while we do the assembly process. Now using the direct stiffness, of course, we have to add these all three members stiffness matrix. So total stiffness matrix will be K is equal to K13 plus K4 K34 plus K42. So of course, direct addition was not possible because numbers, node numbers are different and relevant nodal displacements will be different. So as we have learned that we will expand this matrix in such a way that to the size of the global stiffness matrix, and also it should follow the proper numbering. So let's say 1 and 3. So what we do is we introduce zeros at 2 and 4, the second column and second row. This is the second column we have to introduce, and then second row members should be 0. Then fourth row and fourth column should be 0. And we place our, whatever the stiffness coefficients at the relevant position, that is, sorry, fourth column I have to make 0. Yes. So 200 minus 200 plus 200, like this. So 1, 2, 3, 4 here. Okay. And here also it will be now 1, 2, 3, 4. Similarly, we have to expand the second one, 3 and 4. So we write, this was our K13. Please understand, K13. Then we write K34. So what we do is we have to expand the matrix, bring first column and row 0, then second column and second row 0, and place the remaining coefficients at third and fourth places. 4, 400 minus 400, 400. And the last one, that is K42, can be written second and fourth. So we write, if you think of 1, 2, 3, 4, first and third should be 0. First and third. Okay, so third column and third row. This is the third column and third row. So it's fourth and second. So is it possible for us to write, if we are going to interchange rows and column, then it is possible. But it turns out to be, if we write 2 and 4, you can interchange rows and column to write this. So it will be minus 600, minus 600 will be here. Then at fourth position, it should be 600. Second position, it is 600, then minus 600 minus. I think if you interchange rows and column, it turns out to be the same. So we write 600 minus 600 minus 600, 600. You can check it yourself. If you want to bring this here and bring this here. So direct addition of this now is possible, 1, 2, 3, 4, because all our members are written in a 1, 2, 3, 4 way. So we start writing the addition of this. The final matrix is becoming total K matrix will be 200, 0, minus 200, 0, 0, then here plus 600, this member, then 0, minus 600, this member, then minus 200, 0, 200 plus 400, 200 plus 400. Then minus 400, 0 minus 600, minus 400 from here. Then 600 plus 400, the last term, 600 plus 400. This is simple matrix addition. And on the right hand side, of course, this was the K matrix, total stiffness matrix of the assemblage spring. So multiply this with U1, U2, U3, U4. These are the deformations. And on the left hand side, of course, there are forces. So let's say Fx1, Fx2, Fx3, Fx4. Now joint 1 and 2 are fixed. Joint 1 and 2 are fixed in the original spring. You can see here 1 and 2. So of course U1 and U2 will be 0. So as I told you, we can do the partition from the first two rows and first two columns. And what is left here with us is this matrix, which is going to be useful for determining U3 and U4. So I'm writing that partition matrix now separately. The total is 600 here, minus 400 here, minus 400, and 1000. So U3 and U4, here I can write. Now there will be F3 and F4. You can check whether F3 and F4 is there any load. Of course, node 3, F3 will be 0, but F4 is definitely going to be 25. So 25 kilonewton, we will write it in a Newton. It will be 0, 2500. We can write this way. These are the actual real value. And when you invert, you get, do the inversion or solve, we get U3 is equal to 250 by 11 mm and U4 is equal to 375 divided by 11 mm. Now it is also possible for us to determine the reaction. I told you that how we can utilize that equation. The non-zero terms, you can see here the minus 200, this matrix minus 200, 0, 0, minus 600, U3, U4, and on the left hand side F1, F2, Fx1 and Fx2. So Fx1 and Fx2 are the unknown reactive forces. And we can substitute U3, U2 value there. If you substitute and solve this, I mean, it is simply a multiplication of these two quantities. You get Fx1 and 2. So answer for the Fx1 and 2, just try to multiply this. You are getting Fx1 as minus 50,000 divided by 11 Newton. Fx2, you are getting Newton. And of course Fx3 is 0. fx4 So this completes our example. Now, as I told you, even if this was a spring case, now I told you that for the trusses and bar system, bar is something, the element which is subjected to either compression or tension. So, analogy of the spring, this is also elastic bar, and if we consider x1, x2, u2 are the positive forces and displacement, and here let's say x1, u1 are the positive forces and displacement at joint 1 of the bar and joint 2 of the bar. Then similarly, the individual bar element stiffness matrix very similar to the spring. All of you know that how to obtain the stiffness of the bar is, I know that delta is equal to PL by A, and of course we have to consider all the possible cases. Like first we have to, just like we have done in the spring, you allow the deformation of second joint, then you allow the deformation of the first joint, and by doing this process you try to write the equilibrium conditions and try to relate the forces with the displacement. So both the forces will be related with both the displacement, and in the process we will be getting the very same approach. Instead of K, now K is the stiffness of the bar, instead of K we will be using, because there the displacement is, the force and the displacement relation here with us are, when we are allowing unit deformation we are getting stiffness. So the stiffness for the axially loaded member will be A by L. If we put delta is equal to 1, whatever force we are getting, that is your nothing but stiffness, or A by L. P is equal to A by L is your stiffness, that is K. So instead of K we will be substituting A by L. But rest of the things will remain as it is. And when we write the force and deformation formula, we can still use A by L into that formula. Okay. So we will be able to obtain x1, x2. Instead of K, we are writing A by L minus A by L minus A by L plus A by L. And on the right hand side, we have U1, U2. So from the first principle as well as from physical principles, we will be able to obtain just a similar way when we try to write the force and deflection equations. Now, how to use this element stiffness matrix for determining the example, one typical example of the, the whatever unknowns, that is displacements in the bar. So same thing, same approach, slightly a different structure. So let us say I am having a bar of, let us say this is a bar, fixed end, both end, and again I am having the bar with the, where this bar node 2, here I am naming 1, 2, 3, 4, and 2 will be, instead of now spring stiffness I will be using this, but the procedure and everything will remain same. So joint 2 is subjected to axial load acting in the axis of the bar, let us say 15,000 Newton. Again, I may call 1, 2, 3, and the length of the individual bars are given 0.6 meter, 0.6 meter, 0.6 meter. Total length is 1.8 meter. And nodes are 1, 2, 3, 4. Members are 1, 2, 3. So 3 bar assemblage. Okay. And we have to find the stiffness matrix of these. Now the area will be given as 6 into 10 to the power minus 4. Young's modulus, I mean area is into meter square. E is given 2 into 10 to the power 11 Pascal. Okay, let's say for first bar. Okay, for bar 1. For bar 2, let's say it is, sorry, this is for 1 and 2 both. This data is given. And for third bar, the data will be given. A is equal to 6 into 10 to the power, sorry, 12 into 10 to the power minus 4 meter square. And E will be 1 into 10 to the power 11 Pascal. And 1 and 4 nodes are fixed. So we start writing our K equation, of course. K for the first element, K for the second element. K for the first element and second element will be the same. So stiffness matrix, individuals bar stiffness matrix for the first bar and also the second bar, it will be A by L. Okay, AE by L. So substitute a value of A, 6 into 10 to the power minus 4, 2 into 10 to the power 11 divided by 0.6. I have taken out A by L and our matrix is inside, it becomes 1 minus 1 minus 1 1. And this turns out to be 2 into 10 to the power 8. 1 minus 1 minus 1 1. Now for the first bar it is 1 and 2. 1 2. For second bar the node will be related with 2 and 3. 2 and 3. But the same matrix. So it is for K2 and this is for K1. So 1 minus 1 minus 1 1. And K3 will be given. You substitute A by L, that is given data is 1 divided by 0.6. You can write 1 minus 1 minus 1 1. This is related with, of course, 3 and 4. And then total assemblage. You can follow the process which we have learned earlier. It's simple. So K matrix will be obtained for 2 into 10 to the power 8. And now I am adding the by introducing zeros of the non-relevant quantities in all 4 matrices. Okay, size of the matrix, of course, it's 4 by 4 because our kinematic determinacy is 4. But then we will introduce the support and boundary condition later on to reduce the size of the total stiffness matrix. So total stiffness matrix will be given by 1 minus 1 0 0, then minus 1 2. You can check minus 1 0 0, minus 1 2, minus 1 0 0, minus 1 1. Okay. And then of course we will introduce the boundary conditions, that is, as I told you, 1 and 4. So you have to bring the terms node 1 and 4 which are fixed. This was K matrix, so I am writing U1, U2, U3, U4. And on the left hand side there are forces Fx1, Fx2, Fx3, Fx4. And then as I told you, you can interchange the rows. First row, bring first row to third row and bring first column to third column. So there are 2 steps. First bring first row to third and bring third to first. And second, you bring first column to third and bring third column to first position. I gave you the reason behind doing this is we want to bring the, accumulate the zeros quantities at one corner, and then we have to extract the second and third quantity, and by reducing, after reducing, you will be able to get, I am writing the final version of this, turns out to be 2 into 10 to the power 8, 2 minus 1 minus 1, 2. By partitioning the matrix, you get this. And from this, you will be able to get U2 as 0.05 mm. That is 5 into 10 to the power minus 5 meter. And U3, you will be able to get 2 into 10, 2.5 into 10 to the power 5 minus 5 meter, 0.025 mm. So this completes our example for the bar.